Hello everyone, my name is Bhanudas. I am research scholar in Department of Mechanical Engineering, KK Birla Goa campus, Goa. I am working under the guidance of Professor Ranjit Patil sir. Here I am going to give a presentation on CFD modeling and the performance evaluation of a mixed mode forced convection solar tunnel dryer for curry and coriander use. The outline of my presentation. First, I will explain solar drying techniques, then experimental setup, methodology which we have followed, results and discussion, and conclusion. Solar drying techniques. Solar drying technique is a oldest technique which is used to remove the moisture content from the different agriculture products, which increases the shelf life of the particular product. The crop drying techniques can be classified into two categories: open sun drying and closed sun drying. In case of open sun drying, the product which is to be dried is direct spread on the ground and it is directly exposed to the solar radiations for the drying purpose. In case of closed solar drying techniques, the specific device called a solar dryer is used to dry the products using the solar energy. So the solar drying techniques is classified into two categories, that is solar active dryers and solar passive dryers. In case of passive type solar dryers, the movement of the air happens because of natural convection effect. And in case of active type solar dryer, the mechanical device called blower or the fans are used to make the flow of air through the drying chamber. Again, based on the working principle, the passive and active type solar dryers are classified into indirect mode, direct mode, and mixed mode. In case of direct mode, again the product which is to be dried is placed into the drying chamber, and that product is again directly exposed to the solar radiations. So the removal of the moisture content from that product occurs because of direct heating by the solar radiations. But in case of indirect type solar dryers, the product which is to be dried is placed into the drying chamber, and the air which is heated in another component of the drying system, that is called a solar air heater, that made to flow over the drying chamber, and that hot air which is heated into the solar air heater takes the moisture from the product. The mixed mode type solar dryer uses the working principle of both direct and indirect type solar dryers. And if we compare the performance of these three dryers, it is found that mixed mode solar dryers are more effective. So for our study, we have selected mixed mode type solar dryer. This is our experimental setup, which consists of two components. First one, solar air heater, and second one, drying chamber. The solar air heater uh, consists of one absorber plate, which is made up of a copper of having 1 mm thickness, and that absorber plate is coated with selective black color in order to increase the absorptivity. And the glazing for the collector as well as for the drying chamber is made from the glass of having 4 mm thickness. And this dryer chamber consists of tray for keeping the product which is to be dried, and that tray is directly mounted on the weighing balance so that we can measure the weight of the product periodically. Other sensors like temperature sensors, hygrometer, and pyrometer are used to measure the temperatures, humidity, and solar radiations respectively. Basically, how this system works. Initially, the atmospheric air enters into this solar air heater. By using the heat from the solar radiations, the heating of that air happens, and this hot air enters into the drying chamber, which flows over the product. And so that hot air takes moisture or removes moisture from the product, and finally the moisturized air goes out from the outlet which is provided on this dryer chamber. Methodology. In the first step, we designed and developed our drying system, and here we are comparing. Initially, before going to the experimentation, we conducted the CFD simulation for our system. For carrying out the CFD simulation, we generated the geometry and the meshing was created. The material, again we defined the different material properties and applied the boundary conditions. After solving the fluid and heat transfer equations, we got the CFD results. And after completing the CFD simulations, we went for the actual experimentation. During the experimentation, we loaded the our solar dryer with full of its capacity. Basically, we conducted the experimentation on two samples. That is, first one curry leaves and second one coriander leaves. And finally, we have compared the results of CFD and experimental results. So this figure or this figure shows the how we have generated the geometry of the solar drying systems, and this figure shows the meshing. Basically, for conducting this CFD simulation, we have used ICM CFD 14 software. The number of elements was after the meshing 4,95,264, and where the skewness factor was maintained as 0.88. And the purpose of the doing the CFD simulation was to study the distribution of the air and temperature inside the solar air heater as well as inside the drying chamber. And the CFD simulation results shows that the airflow distribution inside the drying chamber was non-uniform, and same results we got for the curry leaves as well as for the coriander leaves. Now, after completing the CFD simulation, we went for the actual experimentation. And during the experimentation, we have monitored different parameters like solar radiations, temperature of the ambient air, temperature of the air inside the drying chamber. Initially, we loaded the drying chamber, we loaded the solar dryer with full of its capacity, and we conducted this experimentation at constant airflow velocity, that is 0.6 meter per second. Air velocity was maintained during the throughout experimentation on coriander leaves as well as on curry leaves. Now this first graph shows the variation of ambient air temperature, temperature of the air inside the drying chamber, and the solar radiations for curry leaves. And it is observed that the ambient temperature increases with increasing the drying time, and also the temperature of the air inside the drying chamber increases with increasing the drying time. In case of solar radiations, the solar radiations increases up to the noon, and after that it falls down. It is observed that the temperature of the air inside the drying chamber remains higher than the ambient air temperature. And from this graph, we observed that the temperature of the air inside the dryer was higher from the ambient air temperature, and its value was 10 to 12 degrees Celsius. Now, this figure shows the variation of relative humidity and the solar radiations with the drying time. Actually, the relative humidity of the air depends on the temperature, and the relative humidity of the air is inversely proportional to the temperature. So from this graph, we can see that as the drying time increases, the temperature of the air increases. So the relative humidity of the ambient air falls down. But in case of relative humidity of the air inside the drying chamber, it is observed that the relative humidity of the air inside the drying chamber increases for the initial period, and it reaches to its maximum value and then it falls down. This is because during the initial phase of the drying, the evaporation of the moisture from the product starts, and that moisture mixes with the air, so that during this period the relative humidity increases. But after reaching certain value, the removal of the moisture from the product decreases, and so that the relative humidity also decreases. Same results we found in case of coriander leaves also. Now this graph shows the uh, comparison of moisture content with the drying time obtained from the experimental results and from the CFD results. From this graph, we can say that the moisture content of the curry leaves, the initial moisture content of the curry leaves was 63.39%, and for the coriander leaves, the initial moisture content was 89.59% on the wet basis. And as the drying process proceeds, the moisture content of the samples decreases. During the initial period, this the maximum slope of the curve indicates that during the initial phase of the drying, the moisture removal rate is high. But after in the later on the drying later on the moisture removal rate slows down. Same results we found in case of uh, coriander leaves also. And again, compared to the values of the moisture content obtained from the experimental results and CFD results, we observed that the average percentage discrepancy between the predicted and experimental values for the moisture content at the normal drying rate for curry leaves and coriander leaves were 6.90 and 7.09 respectively. Now this figure 9 depicts the variation of the drying rate with the drying time. For the initial phase of the drying process, the drying rate was more, and the drying rate decreases at the end of the drying process. This is because for the initial period, the removal of the moisture from the surface of the product occurs, so we are getting maximum drying rate. But later on, once the complete evaporation of the moisture from the surface of the product completes, then the moisture from the internal part of the product comes to the surface, and then its evaporation occurs. So this takes some time. So in the end of the drying process, we are having slow drying rate. Same results we found in case of coriander leaves also. Also we have conducted the nutritional analysis test. This nutritional analysis From this nutritional analysis test, we found that the except moisture content, all other nutritional parameters like protein, fat, fiber, carbohydrates, and energy contents had increased in the dried products. Also from this photographs of the fresh curry leaves and the dried curry leaves, we can say that there is no much more change in the drying. There is no much more change in the color of the dried product. Same nutritional analysis test we have conducted for the coriander leaves also. Again, here we can see that there is no much more change in the color of the dried coriander leaves. And again, except moisture content, the drying all other nutritional parameters had increased in the dried product. Conclusion: after conducting this CFD simulation and experimental results, we found that CFD is one of the major tool that can be used to evaluate the performance of the solar drying systems. And also we observed that the CFD results for curry and coriander leaves in the solar tunnel dryer is comparable with the experimental study. The results obtained from the simulations are in reasonable occurrence with the experimental results, with variation ranging from 5 to 15%. The moisture content of the coriander leaves was reduced from an initial moisture content of 89.59% to 6.59% in 4 hours, and from 63.39% to 4.82% in 3 hours for the curry leaves. Also from the nutritional analysis test, We can say that the higher nutritional concentrations in the dried products have, occurs, and the low moisture content in the dried product vegetables makes them suitable for longer time. That is, solar drying technology is most effective, and that can be used to increase the shelf life of the different agricultural crops. Thank you. These are the references.